Assalamualaikum everyone, this is Juveria Ahmed, roll number 2022 CE10 Computer Engineering student at UED Lahore. So today I will discuss the lecture 20 of CS 5150, which is all about dynamic analysis and testing. In modern software development, various practices and tools ensure quality, performance, and reliability. Continuous integration automates the process of building and testing code to catch issues uh, early and maintain stable releases. Dynamic analysis helps evaluate software behavior during execution using tools like debuggers, memory checkers, and profilers to identify bugs and optimize performance. Techniques like fuzz testing uncover vulnerabilities by testing programs with random inputs, while debugging systematically resolves issues step by step. Performance testing addresses speed and responsiveness challenges, ensuring software meets user expectations and software requirements. Together, these practices form a comprehensive approach to delivering efficient and secure software. So, this is all about the main introduction of this lecture. Now, we will see this lecture in details. Continuous integration. Continuous integration is a development process that involves building and testing the entire system regularly to make sure all parts work well together. It helps find issues early, making it easier and faster to fix them. Imagine a team of developers working on the same app. Each developer writes their own part of code. Without CI, they would manually combine their code later, which could cause problems like bugs or conflicts because one person's changes might break another's work. This process would rely on developers carefully checking everything, which is time consuming and error prone. With CI, every time a developer writes a code, it is automatically added to the shared project called merging and testing using automated software. For example, if a developer adds a new feature, the CI system automatically builds the app and runs tests to ensure nothing is broken. If there is an issue, the system immediately notifies the team so they can fix it right away. This way, CI ensures the code is always up to date and working properly without relying on each developer to manually test and check everything. CI decisions. When setting up continuous integration, teams make decisions about how the system will be organized and tested during the release workflow. They decide how the system should be built step by step and which tests to run at different stages. A common setup includes a pre-submit test suite that checks all code before it is merged. This suite runs quick tests like compiling the code and testing changes that are directly affected. After the code is merged, a post-submit test suite runs this one runs more detailed tests on the specific commits in the main branch called the trunk. If these pass, the commits are marked as green and considered stable. Finally, a release promotion pipeline runs even more extensive tests to ensure the code is ready for release. These tests often require extra resources and check if the system is fully integrated and reliable. This approach ensures quality at every stage of development. Then we have automation, speed, and infrastructure. Automation, speed, and infrastructure are key to making continuous integration effective. All steps like building, testing, and deploying should be automated and reliable to ensure consistency and avoid manual errors. Ideally, the process should be reproducible so the same results can be achieved every time. Speed is also important. Right? Okay. Speed is also important. Steps like building and testing must be very fast so they don't slow down the team. To achieve this, tools like caching previous builds, skipping tests for unaffected parts of the code, and running tasks in parallel can save time. CI systems should work well with tools like variant control and code review to make sure all checks are done before merging or releasing the code. A last, good to know branch helps the team start new work from a stable version of the code, avoiding problems in the main branch. If something breaks, CI tools can track results, read unreliable tests automatically, and find exact the same cause of the issue. Multi-system CI. In a multi-system CI setup, the code is spread across multiple repositories instead of being in one central place, which is like monorepo. This means the system has to combine code from different repositories, which may have different variants updated at different times. It is not practical to run large integration tests for every possible combination of variants. Instead, the goal is to find specific combinations of variants called configurations that are stable and suitable for further testing or release. These configurations are then tested on larger scale to ensure the system works as expected. Now we have dynamic analysis. But before that, let me check if it is recording or not. Yes, it is recording. So now we will restart. Okay. Now dynamic analysis. Dynamic analysis is a method of testing and evaluating software while it is running. It involves analyzing the behavior of the program during execution to identify bugs, performance issues, or security vulnerabilities. Unlike static analysis, which examines the code without running it, dynamic analysis requires the program to execute in a controlled environment. Now, dynamic analysis tools include coverage tools, which check how much of the code is being tested to ensure all parts are working properly. Debuggers, which help find and fix errors in the code by allowing developers to step through it and inspect its behavior. Memory checkers, which detect issues like memory leaks or incorrect memory usage. Sanitizers, which catch problems like invalid memory access, undefined behavior, or data races. Profilers, which analyze the program's performance to identify areas that need optimization, such as slow functions or excessive usage, resource usage. Then we have debugging demo. Debugging is a process of finding and fixing issues in a program by understanding its behavior step by step. First, you observe the test failure to see what went wrong. Then study the test case to understand what it was supposed to do. If there is no crash, use a tool like Valgrind to check for memory-related errors. To dig deeper, you can set breakpoints in the debugger to pause the program at specific points and explore the code stack to see how the program reached that state. If the issue already exists, at this point, set an earlier breakpoint and repeat the process. You can also use tools like RR to reverse the program's execution and trace back the problem. Okay, let's see this example. So in the debugger, there are commands which help systematically locate and fix problems in the program. Use BT to view the stack trace. Use frame and to navigate to a specific function in the stack. Use info locals to see variables in the current function. Use info arguments to check functions arguments. Use p expression to evaluate and print. Use b to set breakpoint and use c to continue. And use reverse count to step backward during execution. First testing. Now we have first testing. First testing is a technique where a program is given random inputs to check how it behaves. The goal is to find issues like crashes or assertion. The goal is to find like crash issues like crashes or assertion violations that could lead to bugs or security vulnerabilities. This method became very popular in 2010s because it is highly effective at uncovering security flaws. Advanced methods like genetic algorithms or neural Networks can also be used to generate inputs that specifically target certain parts of the program, helping to identify issues in less commonly tested areas. What is performance? Bug. A performance bug occurs when a program does not meet the required speed, responsiveness, or smoothness, leading to issues like missing deadlines or failing to satisfy service level arguments. For example, graphical user interface GUIs should respond within 100 millisecond animations should run smoothly at 30 to 60 frames per second, and systems like MIDI or virtual reality VR need even faster responses around 10 milliseconds. Performance bugs can also show up as unexpected slowdowns for certain inputs, leading to issues like denial of service, DOS vulnerabilities. Other problems include performance regressions, inconsistencies across different platforms, or low throughput in high performance computing (HPC). Now we have performance testing challenges. Let me see. We have okay. Now, performance testing faces several challenges that make it difficult to measure and improve system performance effectively. One key question is determining how much improvement is possible. Tools like Amthel's law help identify limits to speed up or from parallelization or local optimizations. Another challenge is identify whether slowdowns are isolated to specific parts of the system or spread out or caused by complex interactions. Reliable measurements Reliable measurements can also be very tricky due to factors like inconsistency, system load, just in time JIT, compilation, non representative datasets, or intrusive testing tools. Testing needs to consider both average performance and worst case scenarios. Additionally, there is often a trade off between reducing response time and increasing data capacity. Addressing these challenges requires careful planning, realistic datasets, and appropriate testing tools. So this is all from this lecture. If you have any problem, you can ask in the comment section. Thank you so much.